Sorry for that. Yes, thank you. Okay, and analogously, we generalized the previous statement to the following hypothesis. So if we have a vibration of n types, where the fiber is an n-1 type. So an n type is just a space that does not have any homotopy groups above dimension n. So these vibrations are classified. By weak functors from B to n-1 groupoids. So we had n equal to 1 and 0 groupoids, or just sets above, and so that's an immediate generalization. So vibrations classified functors. Okay, so that was one thing we did last time. We also talked about negative stuff. And that was the part where I tried to explain that there is only 1 minus 2 category, which is just a point, and there is 2 minus 1 categories, which is just a point and an empty category. So an analogous situation holds for n types. So minus 2 type is just a point. That follows from the fact that it should have a contractible minus 1 homotopy group. And minus 1 type is either a point or an empty set. So here we sort of have this similarity that once again reinforces this Grothendieck's dream idea. Okay. Then we talked about factorizations. So today I will continue to talk about factorizations. Sorry. And I will remind some basic facts about factorizations right now. So let P from E to B be an infinity functor, meaning that it just preserves a composition of morphisms up to higher morphisms. So E is essentially n surjective if for any n morphism and for any n morphism which just in B we have a lift to the category E. So of course here the word essentially and our philosophy implies that we actually do this up to equivalence. So we do not necessarily have strict lift, or the word any means that any up to equivalence. Okay, so let's consider an example, which was already sort of done last time, but I will repeat it anyways. So the simplest kind of categories are just sets. And we can consider a functor between such categories, which is just a map of sets. So it's a map of sets. And so zero surjectivity, or essential zero surjectivity, but I will drop the word essential from now on, is the same as surjectivity on zero morphisms, aka objects. So this is equivalent to ordinary surjectivity. We also have one surjectivity. But since we're working with sets here, the only one morphisms in sets are just identities. So it's surjectivity on identities. Meaning just injectivity. So that is very nice. We obtained injectivity as surjectivity of certain kind. I can explain why one surjectivity is equivalent to injectivity, because if we had an identity f of a is equal to f of b, that means that we should have a lift, and the lift will be necessarily a equals b. So that's just the condition of injectivity. And the best thing about this simple example is that we have a sort of trivial Postnikov tower. We first get a surjective morphism, then we get an injective morphism. We have a unique factorization. And it can be seen that we factorize first by the morphism, which is zero surjective, and then by the morphism, which is one surjective. Or equivalently, we have a factorization by morphism, which is not one surjective and not zero surjective. So this is this guy, this is this guy. What I'm saying now can sound very stupid because this is such a simple example, but later we will see that if we have, in fact, a Postnikov tower of length n, this condition becomes meaningful. So let me do it in a slightly more general context for categories instead of sets. So we go one level higher, we have one morphisms now. So factorization for categories. We have a map, a functor between categories, and we decompose it like this. So here the functor is 0 and 1 surjective, not 2 surjective. Here the functor is 0 or 2 surjective, not 1 surjective. And here we have a functor which is 1, 2 surjective. This sort of suggests a general picture that we in fact should have a tower of the form E equal to En minus 1, etc. E minus 1, E minus 2. And here we should have not n surjective, not n minus 1 surjective, etc. So we just, at each stage of this Postnikov tower, we just drop one surjectivity condition, and we obtain a sort of vibration with the fiber which has only one homotopy group. That's the basic philosophical idea behind all this. So let me write it down. Functor, I mean an infinity functor, of course, forgets purely J stuff if P is isurjective for I not equal J plus 1. So an example, functor gets one stuff if it forgets stuff. So remember that we had this tripartite separation: stuff, properties, structure. So for example, stuff for a group was a set, stuff for properties for a group was so structure was the multiplication, and properties were various properties of this multiplication, i.e. it is unital, it has an inverse, it is associative. So the functor which forgets one stuff forgets stuff, meaning that we forget, for example, the fact that the group was built from a set. Similarly, a functor forgets zero stuff if it forgets structure. For example, we forget that a set was endowed with multiplication. A functor forgets -1 stuff if it forgets properties, -2 stuff if it forgets nothing. So sort of the larger the fiber is, the more things we forget. So here we forget almost everything. We even, for example, if we forget for a group the set from which it was built, we basically forget the group. And here, when the fiber is very small, it consists only of one point, we don't forget anything. So that's once again very trivial, because of course you know that if we have a fibration with a trivial fiber which consists of one point, it is an equivalence. But it is somewhat less trivial if I formulate it like this in categorical context. Okay. So this all put together leads us to the factorization hypothesis. I already stated it in some form. So we have an arbitrary infinity functor between n groupoids. And we want to say that it can be decomposed like this, where Pj forgets purely J stuff. So if we think of it, okay. if we think topologically, we get the following picture. So of course, the diagram remains the same, but the meaning of those maps is somewhat different. So the fiber PI is the following space. And so, yeah, that's the topological picture, and it is very much reminiscent of the Postnikov tower, which we know or we don't know, but there is a Postnikov tower for a map. Especially if it is an n-type, then it is a finite Postnikov. Well, I'm sorry, to speak absolutely correctly, for if we decompose a map like this, it is not called a Postnikov tower, it is called Postnikov-Moore tower. And if B is equal to a point, it is called Postnikov tower, and for n types, the Postnikov tower is finite. Okay, so now I will draw a silly picture. So we may think of studying topological spaces like this. We have a cake which consists of various homotopy groups. And we basically need to understand how to classify all the layer cakes. That is why I wrote at the beginning of today's talk that layer cake philosophy intensifies. So basically we have a layer cake where each layer is just a fiber of Pn, fiber of Pn minus 1, and so on, somewhere there, fiber of P0. And so we want to classify all layer cakes. We do this with two tools. So the first one is are Eilenberg-MacLane spaces. The second one are the glue or just K invariants. So K invariants are thingies that allow us to know how these layers of cake are related to one another. And so that's basically the study of topological spaces for you. But in practice, of course, this is not always realizable. But let me explain how it should work in purely abstract terms. So I'm not saying that it works, but it should work theoretically. Okay, so we have a fibration, EG to EG minus 1, with the fiber that looks like this. So we want to reconstruct EG from EG minus 1 and some additional knowledge. So how can it be done? Well, we can use Galois theory. And how it's going to work? Well, we will have, so if we're given a vibration like this, we may try to construct a classifying map that goes like this. So it goes from the base space to automorphisms of the fiber. So how we should think of the functor K? Let's first of all think that B is an infinity category. Then one morphism in B lifts to one morphism in E. Two morphism to two morphism, and so on. And every lift actually gives us an automorphisms of the fiber, because, well, we know that the lift should, that ends of this morphism should project to the same point. So actually, each lift gives an automorphism of the fiber. So we get this functor, which acts on, so elements of B act on F just by these lifts. And so that's basically the idea behind non-abelian cohomology. So we may now say, it's sort of a definition, very sketchy one, but still a definition. Non-abelian cohomology of B coefficients in automorphisms of F is the set of functors up to the naturally defined equivalence relation of two such functors. So we obviously can twist the functor by equivalence in the base and by an equivalence in automorphisms, and get another functor which is equivalent to the first one. So up to such equivalence, the set denoted by HB out F is a non-abelian cohomology of B with coefficients out F. Okay, so now K invariant is just a class in this, sorry, I think I should write it here. So that's the meaning of K invariants. They're just classes of, this is not exactly K, this is the meaning of this invariance of vibrations. So we have an element in this cohomology thing, which classifies the specific vibration via this map from B to out F, which gives us the vibration. Okay. So now we may classify, so now the layer cakes or spaces are classified by collection of homotopy groups and collection of k invariants, which just belong to h e g minus 1 out of j. So fj is a fiber, but we actually know what this is. This is just an Erlenberg-MacLane space that looks like this. Okay, so let's quickly review what we did here. So assume that we have a vibration that means that for some p in the base space, we have, sorry, for some star in the base space, we have the fiber or this point being the homotopy fiber of this map. If B is connected, and we can assume that it is connected because otherwise we just have to deal with separate connected components. If B is connected, then F lower star, which is just this fiber, does not depend up to homotopy, of course, on the choice of this point star. Now we may classify such bundles, such vibrations, classify vibrations of the form F. Okay, so a more sophisticated way to say it is that we actually have an n plus 1 yeah, so we have sorry. So if F is an n groupoid, we have this home object inside of n plus 1 category of n plus 2 category of n plus 1 groupoids. And this thing here as an n plus 1 category is equivalent to the category of such bundles. So that's a very highbrow way to say the same thing that I just said, that we classify bundles by k invariants, which are just maps from B to out of F. So we want to classify an n groupoid by squashing it down and plus 2 times until we get a point. So how we do it? Well, once again, I drew this diagram. So E is equal to EM. This is just a point. And so this passage from, for example, En to En minus 1 actually on the categorical level can be described like this. Each J isomorphism, since we have groupoids, all morphisms are isomorphisms, becomes a strict equality. So drop-in information is actually drop-in information about how we have equivalences between objects, between morphisms. So that's actually another meaning of this sequence of groupoids or categories, or if we want to call them spaces. That doesn't matter. So now I will try to do an example which illustrates that this approach is somehow reasonable. It works, at least in low-dimensional cases. So so this is basically a theorem on classification of two groups. So there is this result somewhat from group theory, which explains how to classify all two groups, and it has a certain cohomological invariant which describes them. We will now see how to get it. First, I will explain it in purely group theoretic terms, and then later I will actually explain how it is related to this Postnikov business we've been doing for some time. Okay. So once again, we restrict ourselves to the connected case, but it doesn't really matter because otherwise we'll just have to do the work n times instead of one time. Classified, connected to groupoids. So by contracting the level 0, we get, we want to classify, so this is equivalent, two groups, which are just two groupoids with just one zero object. First, how we will do it? So we take P1 of E, which is G. This is a group of one loops. And we take P2 of E, which is A. And this is a group of two morphisms. So those are just self-equivalences of the identity morphism. And finally, we add, not finally, but additionally, we add an action of G on A. So how it is described? Well, first of all, we have two copies of the identity morphism, and we want to get a transformation between them. which will be denoted rho G of A. And so it is equal to the following thing. So here we have J minus 1, and here we have A. So this is how we get to morphism, which is, well, that's basically just conjugation by an element of the group G. And so it coincides with the usual action of P1 on Pi2, Pi1 on Pi2. Another thing we want to get is an associator, which says that multiplication should be associative up to, at least up to equivalence. So an associator is just a thing that does this. And it gives us a map from the third power of the group G to the group A. How this map works? Well, we basically construct a natural transformation of identity that looks like this. So we have a morphism G1, G2, G3 minus 1 to the power minus 1. Here we have G1, G2, G3. And here we also have G1, G2, G3. And between them, we have an associator, which is just this natural transformation described here. Okay, so also alpha should satisfy the pentagonal identity. Which looks like this. So we take 4 elements, G1, G2, G3, G4, G1, G2, G3, 4, G1, G2. And we go like this. So we have maps that do the following thing. And so this is the pentagonal identity, which can be actually written down in additive form, since the group A is abelian, which I will show in a moment. So in the additive form, it looks like this. RG0 acting on alpha of G1, G2, G3. So I'm sorry, I just shifted indices a bit. Instead of 1, 2, 3, 4, we will have 0, 1, 2, 3. Or yeah, minus G0, G1, G2, G3, plus alpha of G0, G1, G2, G3, minus alpha of G0, G1, G2, G3, plus alpha of G0, G1, G2 equal to 0. So that's basically the pentagonal identity. You can see that it is just the difference of 2 ways we can go by this pentagon. But also it is a condition that d alpha is 0, since alpha is actually a 3 co chain on the group G. So it makes sense to require that group cohomology differential is equal to 0, and that's precisely it. And so all this talk leads to the following theorem due to sync. Oops. In bijective. Correspondence. But V A rho alpha, where alpha is an element of this cohomology group. So rho is a representation of G in A, and alpha is just a class in cohomology of such G module. Okay. So now I think, yeah, I suggest we take a break for 5 minutes, and then we will continue, and I will show that in fact A is an abelian group. Right. Okay. Okay, so let's continue. So now I will just give a bit of algebra, something called Ekman-Hilton argument. So it's a nice result, a nice and simple result from algebra, which allows us to show that, for example, P2 of a groupoid is an abelian group. If we're not, of course, we can do it topologically by, moving squares around, but actually we can do it purely categorically. So we may define P2 purely categorically. And we want to understand why this group of two morphisms is actually abelian without appealing to any topological justifications. And so this is afforded by the following lemma. So let X be a set with two operations denoted by star and tensor product, such that first dot and tensor product are unit. Second, we have the following identity. Then they coincide and are commutative and associative. Okay, so let's prove this statement. First, let us show that units of those two operations coincide. This is relatively, well, the whole proof is relatively straightforward, but so by one knot and one tensor product, I denote, yes, I denote units of the respective operations. So we have proven that they have the same unit. And now we want to show that the operation is commutative. Sorry, that, yeah, so we want to show both that operation is commutative and that it coincides with tensor product. Of course, I'm sorry if it confuses someone. There is no tensor product here. It's just my name for this object. So if you want to old times, Zinwatia. So we have AB, which is equal to the following thing. So now I drop this difference between two possible units since they are the same in fact. So we have B tensor A. We have B A. That as B times A. So we've proven that, first of all, A times B is a commutative operation. And also we've proven that it coincides with B O times A. Now we want to show associativity. Associativity. So we do this by performing the following simple trick. We add unit and then write it like this. So this works for an arbitrary unital commutative operation. So we've proven this lemma. Now let me show quickly that, first of all, for ordinary homotopy groups, it implies that is abelian for n greater or equal to 2. We have two operations. So we can take a sphere and we can contract it along the horizontal. Well, actually, we have a lot of operations on two sphere. Like the circle, we have through each point an infinitely many different equatorial circles. So we have an operation which contracts a horizontal circle, and we get this. Or we can contract a vertical circle, and we will get this. So now it is straightforward to see that if we contract once more, then we in fact get a wedge of 4 equal spheres. So those two operations on which give us multiplication in homotopy groups in fact coincide. So this map gives us multiplication homotopy groups. The fact that we have such contraction, and so we have at least two operations on homotopy groups, and therefore higher homotopy groups are abelian. And the same works in category theory, because actually, if we consider, for example, P2 of C, where C is at least two category, then on two morphisms, we have horizontal composition. So we have horizontal composition and horizontal composition or whiskering and vertical composition, or just, well, the most basic form of composition. You put one morphism on top of another and you compose them. And so these two give us two different operations on the set of two isomorphisms, and this endows this group with the structure of an abelian group. So that's basically Edmond-Hilton argument, and it shows that we in fact have an abelian group A as P2 of. So I defined A as being P2 in a categorical sense of this two-group wide E. And we've just shown that it is in fact an abelian group. So my notation for cohomology with coefficients in G modulo A is completely justified. We in fact have an abelian group, and so this notation is also justified. Okay. So now, after Ekman-Hilton argument, we can try to see how this is related to the general Postnikov business we've been doing. Okay. We may consider a Postnikov tower, which looks like this. So this is just one group, just regular group. E is equal to E2. This is E1. So B is just a group. To group F has a form. F is a fiber of this vibration. So F has a form of two category with one object, one morphism, and some abelian group of two morphisms. Morphisms. So this abelian group can be denoted by A. This group can be denoted by G. And so restoring E is the same as understanding how E is built from G and A. So we want to understand basically why a map K from B to this automorphism 3 group of the fiber is the same as the cohomology class inside of third cohomology group of G with coefficients in A. That's our goal. Let's take let's consider B as a space. As a space, a group can be realized as its Erlenbach-MacLane space, G1. And we construct it like this. So we take 0 simplex. We take 1 simplex for each element G and G. We take 2 simplex for each composition. So we have G1, G2, G1, G2. And so we have a tetrahedron for each composition of 3 elements. So that's an associativity condition. Okay. In the same vein, we can do a geometric description of the space F. So it has the form of Eilenberg-MacLane space, but with shifted degree. And we can describe its simplicial structure. So we have 1, 0 simplex, 1, 1 simplex. We have elements, we have triangles labeled by elements of A, and we have tetrahedra for equations of this form. So we have exactly 4 faces of tetrahedra, and so like this face and this face are A1 and A2, and the back faces are A3 and A4. Now we can describe the space, the dilution of this automorphism group. And so as a simplicial set has the form F so just for just regular automorphisms of F, just without any funny business, just salt of the land automorphisms. And also we have triangles for each equation of each equality of this form. And we have tetrahedra labeled by elements of A. With commuting faces. So faces commute. So the classifying map I'm not saying that this last description is trivial, but you'll have to believe me. But you can, as an exercise, you can think about it. Yeah, it's not quite trivial that we get exactly that, but it's somewhat understandable since F is just since this zero cell is just F itself on which we act. The fact that this just automorphisms form H's is also quite clear. The fact that we should have such triangles is also clear since we have associativity. And sorry, since that's just the basic group condition. And this thing here is also should be satisfied since if we act on an element of A, then we should get the same thing no matter the order of operations. Okay, so the classifying map is a weak free functor K from B to this thing here, or equivalently, we can just take the classifying space of everything here, and we get the functor from KG1 to this space here. Simply looks like this. So it is trivial in dimension 0. No interesting zero simplices. So in dimension 1, we get exactly this representation we wanted, maps from G to automorphisms of A, a map from G to automorphisms of A. In dimension 2, we have cells, or rather simplices, that imply that rho is a group homomorphism. So they correspond to identities like this. This is how they're mapped. So we had two simplex here, and it is mapped to a two simplex here, which corresponds to this exact equality. Okay. In dimension 3, have a map tetrahedra EG1, or just G to the power G cube, two elements of A. So elements of A were labeled by this tetrahedra with commuting faces. And so in dimension 3, we get exactly this alpha, which we were desiring to get, this three co-chain on the group G. And so in dimension 4, leaves the pentagonal identity. The alpha is equal to 0. And so schematically, it all looks like this. Okay. So I think that we're almost done for today. I want just to finalize with the moral of the story. So yeah, first of all, we indeed established the fact that it is the same thing. This description via sync theorem, where we have this fourth G, A, rho, and alpha, and this description via Postnikov towers, where we have this K invariant. But the moral of the story for groups is that, in fact, we have an interpretation of Hn of G with coefficients in A. It just classifies groupoids with fiber Ka n minus 1 over Kg1. And so if n is equal to 2, those are just group extensions. So that was two morals of the story. So first of all, Postnikov towers indeed give us a way to classify certain certain groupoids. So we classified two groupoids via Postnikov towers, and another moral of the story is that in fact group cohomology has a very clear interpretation in terms of classifying extensions, but not necessarily of groups, but of groupoids. So that's, I think, of higher groupoids. That's, I think, all that I wanted to say today. Thank you for coming, and I hope I see you in 2 days.
Thank you.